Today's section will talk about derivative as a rate of change. So we'll talk about average velocity on an interval and instantaneous velocity at a point. The instantaneous velocity or rate of change of f with respect to x at point x naught is f prime of x naught, which can be found using the limit definition. F of x naught plus h minus f of x naught over x naught plus h minus x naught, which x naught and x naught cancel. So h approaches 0 tells me that x and x naught are infinitesimally close to each other, infinitely close to each other. They are very, 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 very close to each other. They're very close to each other. So things to remember: derivative at any point is the rate of change of f of x with respect to x. Derivative at any point is rate of change of f of x with respect to x. Rate of change of y with respect to x. Or if your function is a function of time, if independent variable is time, then it would be rate of change of position function with respect to time. Recall the average rate of change of the function over the interval x and x plus h was given by delta y over delta x, f of x plus h minus f of x over h, the slope of secant line we talked about earlier. This formula is used to find the average velocity if function represents motion of the position. We calculate average velocity by doing change in position over change in time, which is a slope formula, difference into y coordinates over difference into x coordinates. If our 2 points are extremely close to each other, then we can estimate the instantaneous rate of change at that point x using this formula. Limit h approaches 0, f of x plus h minus f of x over h. Displacement is a change in position over a time interval. Displacement and distance covered are not the same. So if I start from this point and I go from my house to Yuba College and then I come back to my house, then and I check my position again, my displacement would be 0 because I didn't really move from my position, but I do have some distance covered. I covered some distance, but my displacement will be 0 in that case. Also remember, speed is the absolute value of velocity. So speed is absolute value of velocity. That means your velocity can be positive or negative, but the speed is never negative. So if you throw something in the air, you throw it with some positive velocity. When it's coming down, it's coming with the negative velocity. When we throw an object in the air, it's thrown with a positive velocity. At some point, its velocity becomes 0, and then it starts falling down with a negative velocity. Acceleration at any time t. Acceleration at any time t is a rate of change of velocity. Sorry, I meant to highlight. Rate of change of velocity, which is derivative of velocity with respect to time. Upward direction will be considered positive and downward directions is negative. Some textbooks might take it the other way. If we are throwing an object upwards, we'll throw with the positive velocity. If it's coming down, then we would consider it the negative direction. Jerk is the derivative of acceleration with respect to time. So third derivative of position is called jerk. Marginal cost is the derivative or rate of change of the cost function at that point. It's the cost to produce one more item at a particular level of production. So marginal cost at point 50 tells me how much it's going to cost to make the 51st item. Okay, marginal cost at 50 can be very, very different from marginal cost at 2000. Average cost is the total cost divided by the number of items, and it's represented with CX using the bar on the top. That's the average cost. Marginal cost is the C prime of X, which is derivative of C of X at a particular level of production. Motion under influence of gravity. Galileo discovered that the height S of t and velocity v of t at time t seconds of an object tossed vertically in the air near Earth's surface are given by the formula here. Memorize these two formulas. Actually, you don't need to remember both, but just remember the position formula. This is for the position S of t. Position S of t depends on the time. It's S naught. S naught is initial position, the height from which is thrown, and V naught, I don't have that written on the next page. So V naught is the initial velocity, and G, acceleration of gravity, is 9.8 meters per second square. 9.8 meters per second square. Okay, so S naught plus V naught t minus 1/2 GT square, that's going to be the position function, and this will be the velocity function. If I go ahead and do the derivative of position function, if we do ds dt, because s naught initial height is a constant, that is going to become 0. ds dt would be s naught will become 0, and it would be v naught minus 1/2, and 2 comes in the front times g. So ds dt, which is velocity, is going to equal v naught minus gt, because it was t squared, v naught minus gt. Now also remember, g is 9.8 meters per second square if we are talking about if our distance is given in terms of meters, but g will be 32 feet per second square, 32 feet per second square if the distance is given in terms of feet. Okay, 32 feet per second square if the distance is given in terms of feet. Then if it's given in terms of meters, then 9.8 meters per second square. Let's look at some examples. Find the rate of change of area of a square with the side 6. Rate of change of area of the square with the side 6. Then find the rate of change when s is 10 centimeters. The rate at which area is changing when your square is this big, if you increase the side by 1, it is going to gain some area. But so let's say your side was s is equal to 2, and we increase the s by 1, the new area is bigger. But if your side was 5, and now you increase the s by 1, you will gain bigger area now. So your gain would be bigger now. So rate of change is different, depends on the side of the square. So area is s squared, dA ds would be 2s. If I do the derivative with respect to s, 2s. So dA ds, the rate of change of area with respect to side, when side is 6, is going to be 2 times 6, which is 12 units. 12 units in that case. But if my area, if the side is 10, then the rate of change will be 20 units. So 20 units squared. So area units are centimeter squared, and the side units are per centimeter. So centimeter squared per centimeter, so that would be 12 centimeter. This will be 20 centimeter. Rate of change with respect to the side. Okay. All right, so next we are talking about find the rate of change surface area of a sphere with respect to r when a is 4 pi r squared. You may not be given the area of the sphere formula, so make sure you memorize from geometry. 4 pi r square is the area of square. dA dr, we are doing the derivative with respect to radius. We want to find out what's the rate of change with respect to the radius. Okay, so that would be 8 pi r, and we want to find out when r is 2 and when r is 4, what is the rate of change. When r is 2 would be 16 pi. When r is 4, this is dr. When r is 4 would be 32 pi. So you can see the area is growing much faster when the radius is 2 as compared to when radius was 2. It's growing twice as fast. Okay, next example. The temperature in degrees Celsius of an object at time t in minutes. So we are given the units of time, and we're given the units of temperature is given by this function. And it's only true when t lies between 0 to 20. If temperature, that lowercase t is the time. When time is past 20 minutes, this function is not true anymore. So we cannot use this function. That's what this means. This is the domain given to us, that this function is only valid between the t equals 0 to 20. At what rate is the temperature cooling or the object cooling when t is 10? Okay, so dt over dt, which is derivative of temperature with respect to time. And don't think this is just saying that the temperature is a function of time. The temperature is dependent variable, time is independent variable. dt over dt is going to be, that is 2 times 3 would be 6 over 8t minus 15. And we want to find out when t is 10, so dt over dt when t is 10 would be 6 over 8 times 10 minus 15. Let's go ahead and simplify. 5, 2, 30 over 2 minus 15. 30 over 2 minus 15, let's see, what does that turn out to be? 30 or 2 times 3 is 6. We could do that here. 15 minus 15. That doesn't look right to me. So 3. Oh, I see. This is 2 times 3 is 6. 6 over 8. 6 over 8 is 3/4. Yeah, 3/4 t. So that is, let's go ahead and take another look at it. Okay, dt over dt is, at t is equal to 10, would be 3/4 times t is 10 minus 15. Yep, that is correct. Okay, 3/4 times 10 minus 15. So 4 and 10 we can divide, which would be 2 times 2 is 4, 5, and that's 15 over 2 minus 15. That is negative 7.5. So negative 7.5 degrees Celsius per minute. This is the rate of change of the area as the time is progressing. Rate of change of the area as the time is progressing. Okay, for the speed s between 30 and 75 miles per hour, the stopping distance f for automobile brakes are approximated by this function. So this function is only true when the speed is between 30 and 75. If speed is different, then this function will not hold true. For s is equal to 60 miles per hour, first estimate the change in stopping distance if speed is increased by 1 miles per hour. So when we are estimating, we can use the derivative. If I do f prime of 60, that is going to be, f prime of 60 is going to be the rate of change if the speed is increased by 1 miles per hour. So this is going to tell me the rate of change when speed is gone from 60 to 61, because it gives you the next point. F prime of 60, that would be the way to estimate the change in stopping distance. So let's go ahead and find f prime of s and then find f prime of 60. So that would be 1.1 plus 0.05 times 2. That would be 0.05 times 2 is 0.10 s. So if I plug a 60 here, 1.1 plus 0.10 s. 1.1 plus 0.10 times 60, that is 7.1. So that turns out to be 7.1. That is my estimate, 7.1. And what's going to be the units here? The units would be 7.1 feet per 7.1 feet per mile. That's the stopping distance per mile. This distance is in feet. So 7.1, approximately 7.1 feet per mile. That's how much, if you increase the speed, then this is the rate at which stopping distance is increasing. If you're going faster, it's going to take you longer to stop. For part B, compare your estimate with actual increase in stopping distance. So how do we find the actual increase in stopping distance? We can find the stopping distance at 61 minus stopping distance at 60, and that's going to give me the actual stopping distance. So all I have to do is plug 1.1 times 61 plus 0.05 times 61 squared minus 1.1 times 60 plus 0.05 times 60 squared. Okay, let's see, what does that leave me with? Go ahead and grab a calculator and plug these into the calculator. 1.1 times 61 plus it turns out to be 7.15 feet. 7.15 feet. So if my estimate is pretty good using the derivative. 7.15 feet is the actual distance, and my estimate was 7.1 feet per mile. So as the speed is increased by 1 mile, then rate of change, or the stopping distance, increases by 7.15 feet. Check out another example. A bullet is fired in the air vertically from ground with an initial velocity of 300 meters per second. Okay, so it's fired from ground. We know the position function S of t is S naught plus V naught t minus S naught plus V naught t minus 1/2 gt squared. And this is my position function. So initial height is 0 because I'm firing from ground. Velocity initial is 300, and the distance is in meters, so g will be 9.8 t squared. So the position function in this case turns out to be 300 t minus 9.8 divided by 2 is 4.9 t squared. 300t minus 4.9 t squared. This is my position function for this object. Position function for this object. Whatever bullet I'm throwing in the air, this is the position function. So what are we trying to find here? Find the bullet's maximum velocity and maximum height. So what's the maximum velocity and what's maximum height? Let's first talk about maximum height. When does a parabola reach the maximum height? So if I throw a bullet in the air, it's going up for some time, and then eventually it's going to start coming down. It is going to have the maximum height at this point. What is going to be the derivative at that point? Derivative of position function or velocity at this point would be 0. So you throw the object with the positive velocity. At some point, velocity becomes 0. That's when you have the maximum height, and then it starts falling down. So at maximum height, the velocity is 0, or we can say the derivative is 0. At maximum height, velocity is 0, or we can say ds dt is 0. So let's go ahead and set the derivative equal to 0 and solve it. S prime of t, which is ds dt, which is the velocity at time t, that's going to be 300 minus 4.9 times 2 is 9.8 t. Now we're going to set it equal to 0. That's going to set S prime of t equal to 0, and that's going to give me 300 minus 9.8 t is 0. 9.8 t is 300. T comes out to be 9.8 divided by 300 divided by 9.8. 300 divided by 9.8, and that is 30.6 seconds. So that means that's unit S, 30.6 seconds. So that means the object, the bullet, reaches the maximum height when the time is 30.6 seconds. When time is 30.6 seconds, the bullet is at maximum height. So how do we find that when time is 30.6 seconds, the bullet is at maximum height? So we can find the height or the position when time is 30.6. So position when time is 30.6, go ahead and plug into the position function. We have that earlier, we found it. That's going to leave me with 300 times 30.6 minus 4.9 times 30.6 squared. And that turns out to be That turns out to be 4592 meters. So 4592 meters. That's the maximum height for the bullet. Maximum height. That was one thing we were being asked in the problem. What is the maximum height? And when does it reach the maximum height? It reaches the maximum height when t is 30.6. When t is 30.6 seconds. So 30.6 seconds after we throw the bullet in the air, it is going to be at the maximum height, and then it's going to start falling down. There's another part here. Find the bullet's maximum velocity. Well, the maximum velocity is, let's look at the velocity function. The velocity function for the bullet is here. So v of t, to find maximum velocity, let's look at the velocity function. Velocity function is v of t 300 minus 9.8 t, right? 300 minus 9.8 t. That is the velocity function. So this function is going to have maximum velocity because time is always positive, so it's actually decreasing. So maximum velocity is when time is 0. Maximum velocity would be 300 meters per second. 300 meters per second will be the maximum velocity. That's when we actually threw it up in the air. After that, the velocity started decreasing. Another example, similar to the one we just did. The good thing is the function is given to me. The position function is 160t minus 16t squared. So a dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second. It reaches the height of this after t seconds. How high does the rock go? So for part 1, we want to find out the maximum height. How do we find the maximum height? The maximum height is when the velocity is equal to 0. So start by, this is s, position function, ds dt is the velocity function, and that's going to be 160 minus 32t. So ds dt is 0. ds dt is 0 when 160 minus 32t is 0. 160 is equal to 32t. T is equal to 160 divided by 32, and that is 160 divided by 32. 5. That's going to be after 5 seconds, the object is at maximum height. So after 5 seconds, the height is maximum after 5 seconds of throw. So we can find the height after 5 seconds would be 160 times 5 minus 16 times 5 squared. That's going to tell me what is the height when time is 5 seconds, and that's going to be my maximum height. So 160 times 5. 160 times 5 minus, that turns out to be 400 feet. So maximum height is 400 feet. And that's going to be our maximum height. So that's the part A. Part B. What's the velocity and speed of the rock when it is 256 feet above the ground on way up? Okay, so for part B or part 2, we're looking for when it's 256 feet up. When this is the position, what is the velocity? Okay, so let's check. When is this position for the object? So 256 is the position, but when does it happen? Let's find that time. 160t minus 16t squared. Now we're going to solve this function. 16t squared minus 160t plus 256 is equal to 0. Now solve it. I think we can divide everything with a 16 here to make my life easier. And that leaves me with t squared minus 10t, and 256 divided by 16 is 16. And there's a 0 on the right hand side. Factor t minus 8, t minus 2 is 0, t is equal to 2 and 8. So this happens after 2 seconds and after 8 seconds. Because after 5 seconds, the object is at maximum height. Okay, so we need to find out the velocity when object is going up, because this is when it's going up, and it's going to be a positive velocity when it's going up. So find out the velocity after 2 seconds. Velocity at t is equal to 2. We already found the velocity function earlier. That is 160 minus 32t. 160 minus 32 times 2, which is 160 minus 64. 160 minus 64 is going to be 96 feet per second. And that's the velocity when time is 2, when the object is at 256 feet above the ground. For part C, what's the acceleration of rock at any time during the flight? So acceleration is the derivative of velocity. So acceleration is derivative of velocity. And velocity is, we have it here, 160 minus 32t. So the acceleration is 100, nope, it would be negative 32. Acceleration is whole time meters per second squared. Negative 32 meters per second squared. It's negative when the object is going up, it's negative, and when the object is coming down, the acceleration is still negative. Because the rate of change of velocity is acceleration. When the object is going up, the velocity is decreasing. That's why acceleration is negative. When the object is coming down, velocity is negative. That's why the acceleration is negative, because it's rate of change of velocity. Now, last part, when does a rock hit the ground? The rock hits the ground, so that's part D, when height is 0. Rock hits ground when the height is 0, when h is 0 or s is 0. We are representing the position function using s here. So s is 160t minus 16t squared. 160t minus 16t squared is 0. So we'll find out the time when position is 0. We can divide both sides with 16, and that leaves me with 10t minus t squared is 0. We can factor t out. Factor a t out, and that's going to leave me with 10 minus t is 0. So either when t is 0 or when t is 10. So object comes back on the ground. T is equal to 0 when it started. So t is equal to 10 is the time when it comes back to the ground. And that's going to be 10 seconds. 10 seconds. Okay, that is a pretty similar problem. Here's another one. We'll take a look at this last problem. Marginal cost is the rate of change of cost at a particular level of production. So this problem, C of x, we're given a cost function to produce x radiators when 8 to 30 radiators are produced. That means this function is only valid between 8 to 30 radiators. For less than 8 radiators, this function is not going to work. For more than 30 radiators, this function is not going to work. So we're given the domain here. That's what 8 to 30 means. Find the average cost and marginal cost when the production level is 20 radiators. Okay, let's first find the average cost. The average cost is C prime of x, which is the total cost divided by the number of items made. So cost of 20 items divided by 20, that's going to give me the average cost. The cost of 20 items would be 20 to the third power minus 6, 20 to the second power plus 15 times 20 divided by 20. Okay, so use a fraction bar, 20 to the third power minus 6 times 20 to the second power plus 15 times 20. And in the denominator, I'm going to have 20. Gives me 295. So $295 is the average cost. Average cost, that's the cost of each radiator when 8 to 30 radiators are made. Okay, now we are also looking for marginal cost. The marginal cost is the derivative of the cost function at that level of production. And marginal cost is going to tell us what is it going to cost to make the 21st product. Okay, marginal cost is going to tell us the cost to make the 21st product, the cost to make the next product. So C prime of x is going to be, this is, we just did the average cost, and now we're looking at the marginal cost. Okay, marginal cost C prime of x is 3x squared minus 12x plus 15, and we want to find the marginal cost at the production level of 20. So that's going to tell me how much it's going to cost to make the 21st item. 3 times 20 squared minus 12 times 20 plus 15. Let's go ahead and check that out. What does it turn out to be? 3 times 20 squared minus 12 times 20 plus 15. That turns out to be $975. Ouch, that's going to hurt. To make the next item, it's going to cost $975. That's a lot of money as compared to the average cost of each product when 8 to 30 radiators are made. So that doesn't seem to be a good option to go ahead and make the next item here. Now, the next part, find the average cost and marginal cost. Let's also look at the actual cost. How much does it cost to make the 21st item? That's also because this marginal cost tells me the rate of change of cost for the next item. Marginal cost at x equals 20 is telling me the cost to make the 21st item. Let's find the actual cost to make 21st item. Actual cost to make 21st item. The actual cost to make 21st item is going to be C of 21 minus C of 20. So if we subtract the cost to make 21 items minus cost to make 20 items, then it's going to give me the difference. That's going to be the cost to make 21st item. So 21 to the third power. 21 to the third power minus 6 times 21 to the second power plus 15 times 21 minus 20 to the third power minus 6 times 20 squared plus 15 times 20. And go ahead and use the calculator, plug them in and find out what is the actual cost to make the 21st item. Okay, looks like it turns out to be 1030. 1030 is the actual cost to make 21st item, and our estimate using the marginal cost was pretty close. We had a pretty good estimate to make the next item. The actual cost is 1030. Our estimate using the derivative was 975. Pretty close, good estimate. So it seems like for this business it's not a good idea to produce any more than 20 items because it's not beneficial.